Okay, thank you, everyone. Good afternoon again. Our second speaker in this afternoon session is Professor Otared Kavian. It's a pleasure for us receive here Professor Kavian. Is an emeritus professor at Université de Versailles. Kavian earned his PhD in 85, okay, from the Université Paris at Marie Curie. Under the supervision of Professor Brezis. Otared does research in applied mathematics with emphasis on stabilization problem. Today, Professor Kavian will give us this great opportunity to attend his lecture, Polynomial Stability of an Abstract System with Local Damping. Thank you, Professor, for accepting to participate in this event.
Okay. Thank you, Roberto, for the nice presentation. I thank all the organizers who give me the opportunity to present my work here. Of course, these non-local seminars are very nice because it gives you the opportunity to be at home and talk about some interesting problems from all over the world. But actually, I regret somehow this kind of seminars because it doesn't allow us to travel to Sevilla or Rio de Janeiro or elsewhere. So it's very good for the politicians who pay research, but for us, it lacks something. Okay, so I'm going to, okay, so, okay, there is a problem here. I don't see. Oh, okay.
Yes. Does it work?
Okay, so, yes.
Yes.
Okay, so do you see my presentation?
Yeah.
Okay. So I'm going to talk about polynomial stability of a sort of abstract wave equation. And okay, so there is a problem with okay, it doesn't react immediately. So it's a joint work with Qiong Zhang, who is at the Beijing Institute of Technology in China. The paper was published 2 years ago. And the problem is the following. We consider a bounded domain of Rn and the classical Laplacian acting on omega. And we consider two functions, B1 and B2, which are positive. And then we study the wave equation associated to the Laplacian. So here there is a term which is this one, which presents a certain type of damping. One is just a multiple of the velocity, and the other one is a more complicated damping, okay? Oh, here is the mistake is gradient of u sub t. So I made a mistake here, is u sub t. So, okay. So now we, oops, I don't know why it doesn't accept to. Okay, so I'm sorry, my computer doesn't react.
You can, I think you can click in the hand in close. If you look in the first, there is the page 542. You can just click in the hand. Click here in one hand here. There is minus and plus. Close to minus, there is a hand. You can just try to click in this hand. Yes.
There is a hand here. Okay.
Yeah, try. And now see what's happened when you.
Yes. Okay. Yes. Yes. Thank you. Okay. Yes. Okay. So again, I do Command L. This one. Now it's fine. Okay. Yes.
Yes, Professor, yes.
Yes. So if we consider the energy attributed to this wave equation, then the energy decays in this way. It is easily seen that if the coefficients B1 and B2 are strictly positive, then we have an exponential decay to zero of the energy. Okay. And in fact, there are other properties of the underlying semigroup which have been studied extensively. But here we are going to consider the case where B1 or B2 are just strictly positive on a subdomain of omega. Okay, and we want to study whether we can find an exponent m such that the energy decays polynomially. This means in this manner. Okay. As we shall see, the exponent m depends in a very complicated way on the eigenvalues and eigenfunctions of the Laplacian and how they behave, in fact, on the domain where the damping takes place. Okay. Okay, again, it's so I don't know why. Apparently there is a problem between Acrobat Reader and
Try to use in this way without any Command L. Let's check.
Okay, this way. Yes, this way. Okay.
Okay.
So what we are going to use is the fact that when the resolvent set of the operator A is completely contained in the imaginary axis of the complex plane, then one knows that the semigroup converges to zero as t goes to infinity. And then there have been many works by many authors who have studied in what manner the behavior of the resolvent of A on the imaginary axis will imply a certain decay of the semigroup. More precisely, we are going to use this result by Borichev and Tomilov from 2008, which states that if we know that the resolvent behaves like 1 plus omega to the power m, this means that divided by this is bounded, then the semigroup is going to converge to zero polynomially as 1 plus t to the power 1 over m. Okay. So what we are going to do is to see under which circumstances, under which conditions imposed on the coefficients B1 and B2, we can have an estimate like the one which is here, that is the resolvent is bounded by 1 plus omega to the power m. Okay. So our assumptions are the following. We assume that the operator L is self-adjoint, has a compact resolvent. Its spectrum is denoted by lambda k, and each eigenvalue has multiplicity mk. So in this notation, we are denoting lambda k as being different from lambda k plus 1, but each eigenvalue may have a certain multiplicity. And also we denote by lambda 0 equal to 0. Then we consider an operator B, which maps the Hilbert space H1 into H minus 1. So I did Okay, I didn't say what was H1 because, okay. So H1 is the domain of L1/2. H minus 1 is the dual of this one. And H0 is the analogous of L2 of omega space, okay? So, and the operator A we are considering is the matrix, which is 0 minus I, LB, and the wave equation, which was here, this wave equation, can be written as d over dtu of t plus au equals to 0, okay? Where u, capital U is u dtu, okay? So now, the assumptions we have is that L is a self-adjoint operator, B is a non-negative bounded operator from H1 to H minus 1, which is self-adjoint in this sense, B times phi is positive, and B phi psi is the same as B psi phi conjugate. Now we assume that the operator B is non-degenerate in the sense that when you take the minimum of this B phi on the eigenspace associated to lambda k, this number is positive. It may converge to 0, but at a certain rate, which will be precise later on, okay? So our main result is the following. We assume that lambda k over lambda k plus 1 has an infimum, which is strictly positive. This means that essentially lambda k over lambda k plus 1 is of order 1. In most cases, this is equal to 1. Okay, the limit of lambda k over lambda k plus 1 is equal to 1. Okay. So the other assumption is that the number beta k, which is the minimum of B phi phi on the eigenspace lambda corresponding to lambda k, this number is like lambda k to the power gamma 0. And finally, we assume that the difference between the eigenvalues is comparable to a power of the eigenvalues. So more precisely, lambda k minus 1 over lambda k minus lambda k1 is of order lambda k to the power gamma 1. Okay? So with this assumption, if we denote M as being 3 minus 2 gamma 0 for gamma 1, then we have that the resolvent increases at most like 1 plus omega to the power m. Okay. So these are some comments about our assumption. So the the condition 11, which is here, means that in fact B does not vanish on the finite dimensional eigenspace corresponding to lambda k. Okay, beta k might be small, but is never equal to 0. Okay, and the condition which says that this number lambda star is positive is always satisfied for the elliptic operators we have. Okay. Okay. So now I would like to give an example in one case in order to see how the eigenvalues enter the situation. Consider the case where the operator B is precisely a multiple of the operator L. For instance, if L is the Laplacian, take the case where B is a multiple of the Laplacian. Okay. In this case, one can determine completely the spectrum of the operator A. So the spectrum is given by these numbers, which are eigenvalues, and an accumulation point, which is 1 over B0. Okay. In this case, one sees that the spectrum of A is either contained in the half-line delta 0 plus infinity of the real line, or in the right half plane of the complex plane, real of zeta larger than delta 0. Okay, so in either of these cases, one sees that the exponential, the operator exponential of minus TA is analytic and exponentially decaying, the decay rate being exponential of minus delta 0 t. Okay, but now if we, instead of the operator B, which is a multiple of the operator L, we have something which has nothing to do with this operator L, the analysis of the spectrum is quite rather impossible. So the only thing we are going to be able to do is to show that the resolvent set is bounded on the imaginary axis. Okay. So we are going to use this the classical result, which characterizes the operators which are which have closed range, and they have a kernel which is equal to 0. Okay. So we set the Hilbert space H as being H1 times H0. So A is this matrix, and the domain of A is this. One checks that the adjoint of the operator is written in this way, and we check also that the kernel of A and A star are equal to 0, and also that the operator A is a closed operator. Of course, A star is automatically closed. So therefore, thanks to the Banach theorem, which is here, we know that the operator A minus 1 exists. This means that 0 does not belong to the spectrum of A. Now we are going to write the interval 0 plus infinity as being a union of a small interval and the interval lambda k minus 1, lambda k plus 1. And for each omega such that omega squared belongs to either of these intervals, we are going to obtain an estimate of the resolvent on this interval. Okay, so we denote this number alpha j of omega when omega squared is not equal to lambda j, of course. And first, we are going to decompose the space H0 into 3 subspaces. One is EK, which are the corresponding eigenspaces where J is less than K minus 1. And then we have Fk, which is the orthogonal of EK plus 1. And for convenience, we denote by E1 equals to 0. Okay. So now we take omega squared in the interval lambda k minus 1, lambda k plus 1. And we check that we have this coercivity property. Okay. So on the space EK, we have omega squared identity minus L, which is coercive with an exponent, coefficient 1 over alpha k minus 1. And on the space Fk, this is the operator L minus omega squared I, which is coercive, okay? So now, once we have this, in order to solve A minus I omega identity UV equals to Fg, we are going to decompose the function U and V in the space H0 as being the sum of 3 parts. One in AK, one in the kernel of kernel of A minus lambda K, L minus lambda K identity, and one in Fk, okay? So since we have these equations, we have to set H as being the second, this part, and we have to solve Lu minus omega squared U minus I omega B equals to H. So we have to estimate the norm of U in this space, okay? Of course, you see the problem here is that if omega squared can be equal to one of the eigenvalues of L, then it is not easy to find an a priori estimate on U. So to this end, first, we consider the case omega squared less than lambda 1 over 2. In this case, using the property that the operator L minus omega squared identity is coercive, we get this, this property, okay? So we have an estimate. So now we can consider the case where omega squared is far from 0, so is say bigger than lambda 1 over 2. So in this case, we multiply this equation, which is here, by the function U, and we take the imaginary part, okay? So since we have this omega which is not 0, so this one is not equal to 0. Therefore, we have that this estimate. But you see here, BUU is not definite positive. So this inequality is not enough in order to obtain an estimate on U, okay? Nevertheless, by decomposing U in 3 parts, Y plus T times phi plus Z, where Y and Z are in EK, Fk, and phi belongs to N, the kernel of L minus lambda K identity, with norm of phi equals to 1. Phi, of course, depends on H. But the only thing we know is that the norm of phi is equal to 1. Okay? So we don't have any other information. We have just the norm of phi, which is equal to 1. So we have this equation. First, we obtain an estimate on Y, just by multiplying this by minus Y, because this will give you an estimate on Y, norm of Y squared, and the other two are equal to 0, okay? And now we are going to use the fact that we had the estimate, which was here. Therefore, finally, we obtain an estimate on Y with a coefficient which is here. The same thing with Z. And now we have an estimate which depends on norm of U, but the power 1/2 on the right-hand side here. And these things are orthogonal to, these things and this thing are orthogonal to phi. So we multiply now by another term, which is the sine of T times phi, and then we obtain an estimate on T, and then on the function U, okay? But of course, at this point, the estimate on U has a term which is norm of u to the power 1/2. You see here, so this problem is that here we don't have a constant. We have norm of u to the 1/2. But nevertheless, by using the Young's inequality, we obtain that norm of u in H1 is less than some constant, etc. Okay, and by making the calculations, we establish also an estimate in H0 and H1 according to whether the right-hand side belongs to H0 and H1. And finally, we obtain that if M is equal to this constant, then the norm of the resolvent is 1 plus omega to the power M. Okay, so this is the idea of the proof. So now I give some examples in which we can compute the exponents gamma 0, gamma 1, which were introduced previously. So first, in dimension 1, consider a Sturm-Liouville operator, which is here, where A is L infinity is strictly positive and Bj also are positive functions, okay? So first assume that A of x is equal to 1 and the coefficient B2, which is here, is larger than a constant epsilon 0, okay? Here is the subdomain, which can be very small, but delta is fixed, okay? Now, if you consider that the number beta k, which is here, which is defined here, is which is defined there, it is easy to compute and see that beta k is in fact larger than C of delta k squared, and k squared is essentially the eigenvalue, okay? So the exponent gamma 0 is equal to 1, okay? Condition 12 is the fact that the ratio of the eigenvalues converges to 1, okay? And this condition, which is the difference between eigenvalues, the difference between eigenvalues is like k, and therefore we have here something like gamma 1 equals to 1/2. So finally, we obtain that M is equal to 3. Therefore, the solutions of this wave equation converge to 0, like 1 plus t to the power minus 2/3. Okay? For this specific case, in fact, it has been proved that the convergence is like 1 plus t to the power minus 4, but that method cannot be extended to the cases we study here. So I'm going to show the result later. The same when the B2 is equal to 0 and B1 is positive. So here this one is equal to 0, and so the damping is just on the velocity. Okay. In this case, we obtain m equals to 5, the number which is here. Okay. In fact, when the coefficient A is of class C2, it is known that the eigenvalues and eigenfunction and the derivative eigenfunction behave like this. And one can show again that in this case, we have the same exponent of decay. Okay. So in this case, A can be C2, B can be anything, just L infinity. So we have either a decay of order minus 2/3 or a decay of minus 2/5. Okay. And the same holds when we have a coefficient rho of x in front of the second derivative of u in time. And in this case, by changing appropriately the functional spaces, one can show that the same decay rate holds, exactly the same. Okay. But when A and rho are not C2, since we don't know how the eigenvalues, eigenfunctions of Sturm-Liouville operators behave as k goes to infinity, we are not able to adapt our result to that cases. However, there are a few examples in which, for example, A of x is constant, piecewise constant in a finite number of subintervals. Then one can show that the eigenvalues and eigenfunction behave exactly as was mentioned before, and the decay rate for the wave equation holds the same. Okay? So this is the case number. Now, for the two-dimensional case, if we consider a rectangle in R2, or more generally in Rn for n larger or equal than 2, and we consider the Laplacian and the operator B again being something like that. In this case, the eigenvalues are these numbers lambda and tilde. So I put a tilde here in order to emphasize that these are not the eigenvalues we consider, because our eigenvalues are not repeated. Each eigenvalue has a certain multiplicity mk. Okay? Then, if we assume that Xi, the number L1 over L2 squared, is a rational number, then the eigenvalues are not simple in general, apart from the first one by the maximum principle. However, when Xi is not a rational number, then each eigenvalue is simple. In any case, in both cases, the limit of lambda k plus 1 over lambda k is equal to 1 as k goes to infinity. In order to estimate, you see here we need to estimate lambda k minus 1 as k goes to infinity. In order to do that, we have to study the infimum of mu n minus mu m, where mu n is defined in this way, okay? So when the number psi is a rational number, one can show that this number is strictly positive and in fact is larger than 1 over q, while if psi is not rational, then this number is equal to 0. So this means that in the case of a number psi, which is this one, L1 over L2 squared, the eigenvalues are simple, but the difference between eigenvalue converges to 0. So this is going to create some difficulties for us, okay? So in the case where psi is irrational, we have this estimate, and therefore by choosing a special domain, a subdomain where omega 2 is the strip in the rectangle, in this case, one can show that the number beta k is larger than lambda k, okay? So the exponent gamma 0 is equal to 1, and gamma 1 also is equal to 1. And finally, the decay is like the number m is 5, and the decay is 1 plus t to the power minus 2 over 5. However, when b2 is equal to 0, then the number beta k is just larger than some constant. And in this case, the decay rate is going to be 1 plus t to the power minus 2 over 7. And finally, when the number psi is not rational, but it is algebraic of degree greater or equal to 2. So this means psi is the solution of a polynomial with rational coefficient, with integer coefficient, and its degree is the degree of the infimum of the degree of all polynomial for which psi is a 0. So in this case, using Roth's theorem, one can estimate that lambda k plus 1 minus lambda k is larger than a constant which is here. And in this case, when we choose omega 2, a small rectangle contained in omega, we don't need a strip on omega, just a small square is enough. Then we have gamma 0 equal to 1, and gamma 1 is 2 plus, can be taken as 2 plus epsilon over 4. And finally, the decay is 1 plus t to the power minus 2 over 9 plus epsilon. And when B2 is equal to 0 and B1 is not 0, then we have something like a decay like 1 plus t to the power minus 2 over 11 plus epsilon. Okay, and the same can be done for any rectangular domain in Rn. There are some other examples, but they're very specific, so they are not really interesting to talk about. Okay, so I think now I can stop because my time is finished. And so thank you for your attention.
Thank you very much, Professor Kavian. Let's pass for questions or comments. Juan, can you open the... Okay, the microphone is open. If everyone want to say something in the chat, just
What about the optimality of the decay, M?
It's not optimal. Our method does not allow to obtain an optimal because we have to estimate in general how the how this number beta k, which is the minimum of the B phi for free eigenfunction of order for lambda k, how this behaves. Okay. So unless in very specific conditions, this is a very, very general approach. So we cannot have an optimal decay. Okay.
Okay. More questions or comments? Okay. If not, let's say thank you, Professor Kavian, for this nice talk. Thank you.
Thank you for